Okay, we begin our program with one of the biggest questions, that is, what is AI, right? It's a work in progress, but we need to know what we're working on. And I think that actually we've already seen yesterday that there is a wide range of things that we're talking about when we talk about AI, and the devil is in the technological details. It's really important to understand them. And that is a problem, because normally when you talk to a lot of computer scientists and data scientists, they talk in one language and you understand in another language, something that is actually remind me also of the example that is always given about the Chinese room, that someone is like bringing one thing in one language and you gotta get it out in another language, but you're not sure whether you really understand what people are talking about. Therefore, I think that we're really lucky to have Professor Avigdor Gal from the Israeli Technion. Is one of the people that actually managed to create this bridge between computer science and data science, and those of us in the humanities and social science that are not experts in this technology. Professor Gal is an expert in information system and a professor at the Faculty of Industrial Engineering and Management at the Technion. His research focuses on effective methods of integrating data from multiple and diverse sources which affect the way business and consumers seek information on the internet. Professor Gal have published over 100 articles in leading professional journals, but as I said, most importantly, he is one of the few people that I know that know how to bridge this gap between the disciplines. Thank you very much for joining us this morning.
Okay. Good morning, humans. Good morning, artificial creatures. Hi, Siri. I try to do that at least once a day to keep her happy. So, my name is Avigdor Gal, and I come from the Technion, which is a university close by. What I want to talk to you about today is the three different concepts: human intelligence, artificial intelligence, machine learning, and maybe try to figure out who is the winner. So the outline is easy in such talks, because I'm going to talk about human intelligence, then about artificial intelligence, then about machine learning, and then declare the winner. So let's start with human intelligence, which we have a lot of in this room. So have a look at this picture. A woman walks into a room. This may be an airport, or it may be a hospital, or no gender intention, it may be a shopping mall. And this room has one entrance, and at the very end there are two exits, one to the left and one to the right. And how can we tell to which door this lady is heading? Humans. Your turn. Any thoughts? What's that?
I said like bathroom, like at the end of the right.
Yes. Okay. So, but you don't know if she's going there or not, or is there any indication of where this lady is heading? Yeah. Okay. Very good. So right now the lady is standing in the very middle, right? But had she turned a little bit to the right or to the left? Or maybe the way that she is just looking at, maybe that will tell us whether this lady is going right to the right or to the left. Yes?
Also depends a bit where she's
Okay. This may be a lady that follows the crowd or the sales, and wherever there are more sales, you will see more people, and this is where she will be heading. You understand why this is an important question, right? So if this is an airport and we're dealing with security issues and we want to identify maybe a terrorist that is heading to a gate, then we would like to know that. If I have a sale and I want to know whether I can attract enough people and maybe I can push them a little bit to go there. If I'm an elderly person and I'm heading to a place at the house where I might be in danger. So all of this is something that we really care about. For example, here is a solution. If we were to put some instruments at the entrance to the room, let's say a fountain, this is a way of forcing a person to decide ahead of time whether she goes right or left. Lots of assumptions here, right? This is a person that needs to be rational and to use some optimal mechanism in order to go directly to where they're heading. Maybe people are trying to tour around instead, doing some kind of exploration. All of this should be taken into account when I design this kind of an environment. Okay, another story. This is the building of a facility called Dana-Farber in Boston. This is a cancer institute. It's a day hospital. People come in. They come for a treatment. They see a doctor. They see the nurse. They get the chemotherapy, and then they go back home. So in this kind of environments, often we can use maps in order to guide our way. So this is a map that the hospital has. Maybe I'm jumping ahead of myself, but this is based on sensor reading. So the map actually shows you where each of the people are at any point in time. And this can be used by nurses, for example, to locate the next patient and to put them in the right room. So we use this color scheme, like green rooms are empty rooms, yellow rooms are busy, red rooms need to be cleaned. And by doing that, I can look around and I can figure out where I'm going to put a person. So I can use this type of information to enhance the usability of the facility. So for example, instead of assigning rooms for specific doctors, I can do a dynamic assignment where if there is a room empty and the doctor needs to meet with the patient, then I can put them there. And I can do all this kind of decision making based on that, on how many patients can I invite per hour, and whether I'm going to be behind schedule and then I have to call some people to come late, and so on and so forth. Again, we put some intelligence into the way that we handle this scheduling. A third example. Anyone knows where this is? Unless you've heard this before. Now, it's hard to tell, right? It can be anywhere. So this is the city of Dublin. The city of Dublin in Ireland. The city of Dublin has a wide public transportation network. What we see here is kind of a Google map with needles, with pins at the, along the one specific line. And when we deal with transportations, especially in big cities, this is really when we need to invest a lot of intelligence. So usually this is being done by putting everybody at the same room. So this is called the control room, and this is the Dublin control room. And in this room, we can gather information from many different parts of the city. We can also put a radio station in the room itself, and then the people that broadcast information, they can also tell us about the traffic conditions. And this is exactly what happens in Dublin. This is a smaller meeting room next to the bigger one, of which I unfortunately don't have a picture right now. And this is where all things are being done, especially in situations of rush hours, and then in a situation of catastrophes, like car accidents and so on. Okay? So I gave you 3 examples that I'm going to use later, and all of these 3 have in common the fact that as humans, we have invested time and understanding and intelligence to solve problems. Now, moving from human intelligence to artificial intelligence. So, when the area was originally created, the buzzword of artificial intelligence was meant to capture elements of our own intelligence as humans and move them over to the machine. Okay? So it was really about trying to use the intelligence elements of what we conceive to be intelligence and put it into a program. So we had nice examples. Leading examples involved games. We had Deep Blue that was playing chess, and we had later on AlphaGo that was playing Go, and so on and so forth. So typically, researchers would have done that with two main steps. The first step involves modeling. How do we conceive the environment in which we try to solve our problems? So this is a modeling tool for our airport example. So instead of looking at the picture, what I do now, I draw some kind of a small rectangle on the board. I partition it into a grid. And there I can say that I have few paths to get from the start point, which is where the lady standed at the beginning, to one of my two goals. Okay, so with this simple diagram, I managed to capture a lot of the issues that I talked about early on. We have a way of navigating, we have an entrance, we have goals, we have paths that we can take. Now, I can take the image that I had before and illustrate it in this way, where basically putting this fountain is simply disallowing an action. Okay, so now I said that this lady can no longer walk straight because there is something blocking the way. So by adding this little piece on top of that, I basically created a model of the environment. In most cases, models are a simplified way of looking at the world. In some cases, it captures it very well. Now, some models are more difficult to understand and sometimes are more complex. So before I had this spatio-temporal environment that we can easily see by putting something on drawing. Here, when we talked about the hospital situation, we have also the time dimension getting into the picture because, as I've said, some rooms may be occupied at some times and then empty at other times, but a room cannot be double booked, or it can be double booked, it cannot be double used at the same time in this specific example. So to do that, we can generate a model. In this case, this is an interval model, where we basically describe the relationship between different intervals. So you can think of time as being an interval, and obviously what we don't want to get is maybe an overlap. An overlap means that the same room is being used twice at the same time. However, I also don't want to get just two intervals that are very sparse in space. The best thing for me, the most optimal way to assign rooms will be something that one interval starts as soon as the other one finishes. Okay? So again, I'm using this type of model to show the temporal constraints. And this is called Allen algebra, and it was devised many years ago, and it's being used when we try to model temporal relationships. Then we can use that to even get things even more complex. Don't try to understand that too much. There is a point later in the lecture that I really want you to understand. This is not that important. But what we're going to do is we're going to use as another modeling tool something that we call a graph. So a graph has nodes, which are these circles, and it has edges. And basically by that we put constraints. And we can do temporal constraints the same way that we do other types of constraints. And on each of these edges we can put information about what type of overlaps we do. Okay, so we're good so far? These were two examples of how we model the world. Here is another third one that we use when we talk about transportation. We were trying to think about a bus traveling through a city. So there are many ways to think about it. One way is to think about the bus doing separate segments in the city, each one connecting one bus stop to the other. Okay? And we would like to see what happens in between these two stops. You know, a bus can be traveling, or the bus can be standing in a traffic jam, or a bus can be traveling on a public lane while other cars are standing in a traffic jam. All of these things can happen. But as a modeling tool, when we take one tour of a bus and break it into small pieces, then immediately we created a model that we can later use. So maybe for some of these things you would say, oh, that's too simple. Or for other things you would say, this is too complex. And that's true, because our models may change depends on the problem that we try to tackle. But in all these three cases, we start with the model. But we cannot stop there, because our intelligence, whether it is human or artificial, is not just about understanding the environment, but we need to move to the next step. And the next step is about reasoning. So again, this is just images. Don't pay too much attention to it. So as soon as we have a model, we can do some kind of reasoning on top of it. And here is an example. The example that, remember the lady that walked into a room, right? I don't think that you can actually see the connection between what I show here to that lady. But this is what we do when we do an abstraction. What we would like to know is how to redesign the room in a way that would allow us to know as early as possible the goal of that lady. That's, as I said, in security, in safe homes, in hospital. This may be a worthy goal to achieve. And we do that, and this is the first mechanism of artificial intelligence, or the most common one in many years ago, by doing a search over all possibilities. So remember earlier I said we can put a fountain, and then I said when we talk about modeling, we basically prevent certain actions. So think of a world where there are many actions that we can prevent. And we would like to know which are the actions that we need to prevent to increase our understanding of where the lady is heading. So earlier I've shown you the solution already. It was just blocking the way at the entrance, which forces humans to decide whether they go right or left. But to do that, there are many different ways of doing it, and I can show you some of that, which I will not. But basically, I'm doing a search over possibilities, trying to reach the best one that will optimize the goal. So what you see here is a way to illustrate the search. And we call that in computer science a tree, although it is exactly the opposite of the tree because the root is at the top and the leaves are at the bottom. But, well, once you get into that, you really don't see the difference. So at the top, we have the current situation, and then we have edges that lead to the next level. And each other node is a little bit of a change of the model that we had before. The problem is that once we do the model change, we need to understand whether it helps us or not. And that's why we need to go to the lower model, run some kind of a simulation on that, and figure out whether we manage to improve the problem or not. And then you get into all these things that computer scientists typically bitch about, and this is about performance, and it's very hard to get it, and the complexity of the problem is high, and the complexity of the space is high, and so on and so forth. But these are the issues that we need to deal with. Mainly, we are doing reasoning. We need to define a reasoning mechanism over the model that we had before. Okay, here is another type of reasoning. When we look at a model and that, or at an environment like the hospital, it may be too complex for us to understand or to even compute. Because there are many branching theirs, and every person can go either right or left at any point in time. Okay, so trying to take into account all these possible worlds and sometimes even assigning probabilities to that may be too complex. So we're looking at ways to try and simplify models. And what we have here are 5 types of models at the top that is being simplified to one thing at the bottom. So now that you see the one at the bottom, you see 2 rectangles, 2 circles. Looks pretty simple. This is a simplification of all of the 5 that were above. Some talk about activities that are being done simultaneously. Some talk about activities that are being done sequentially. And then when we simplify a model, we always need to ask ourselves, what do we pay? Do we really pay a price for simplifying the model? Because if we manage to pay no price, then the simplified model is better than the more complex one because the computation on top of it is easier. But sometimes we can quantify the amount of loss that we have. So let's say that we invent a measure that we call accuracy, and by using the lower model, we lose 5% of accuracy. Is it worthwhile doing it? What kind of price do we pay? Maybe we still need to do it because we have no other choice, but we know that in general it's going to be 5% less accurate. This is also a good thing to have, and this is also something that comes into the reasoning mechanism. While you reason, you also keep the price at the side to know how much you pay. Okay. And that's the last example of the reasoning. The reason you stare at the reasoning and maybe ask yourself, what am I doing here, is because reasoning is harder than modeling. Reasoning may be more involved, and therefore we need to learn more in order to deal with it. This is a reasoning over the bus traveling through the city. Again, I don't know if you can see the connection between that and a bus. But if you think about those circles as being the stops, and in between the stops, the bus runs through a queuing system, just like a queuing system that you have when you queue for groceries at the supermarket. I know it's not the most trivial way of thinking about a bus traveling through a road as being in a queuing system, but if you think of the road as being a service provider that provides a service at a certain amount of time, and if there are more cars on the road, the service becomes slower, then all of a sudden the connection between that and waiting in the supermarket may be reasonable, or maybe an alternative in nature where water runs through a pipe and so on. Okay? So when you do that, you can say, okay, if each segment by itself has its own problems, we can connect them in some way and see the implications of having problems in one way and how they are propagated into another way. Again, this is all the reasoning that we put on top of the modeling that we had before. Okay. So what we had so far, talked about human intelligence, and you were brave in that. And then we talked about artificial intelligence, and we talked about the 2 main parts of it, the modeling and then the reasoning. This one I need to show. It's really cute and I like it. So if we have these different segments, okay, and let's say that one thing that I want to know whenever I get on a bus is how long I'm going to travel on the bus, right? So this is a typical question, and we have all these tools that answer us. They never correct, right? Unless they are, this is really unreasonable cases. Usually we do get delays and so on, and the system kinds of fixes itself. Now, we were dealing with this situation where we wanted to compute this prediction based on our model. So what we did is, and this is another way of reasoning, look at time as flowing from top to bottom, and the bus traveling not only through space but also through time. And the star represents the bus position right now, and we need to compute how far down the bus will have to go until we reach our goal. So what we do here, and these are the different colors, we took the time it takes a bus to travel, a previous bus to travel through this segment, and we use that as an estimation of how long it's going to take us to travel this segment. Now, I know it sounds simple, And sometimes you may not agree that this works, because if I try it at 6 a.m. and then I'm traveling at rush hour, it will probably not work, right? So it works only under certain conditions. And there is, it's called the snapshot principle in queuing theory, that basically tells you that if you come into a system that is always busy, then the best way for you to understand how long it's going to take you to stay there is to ask the person that is waiting first in line how long they waited, because there is some kind of a steady performance. And then you can use that, but keep that in mind, because I'm going to get back to this example later on. Okay? So, now I'm going to get into machine learning. Okay? And typically I find myself in a situation when I need to explain that AI is not machine learning, and well, it's not really that important. I mean, AI is fine as a concept, unless it limits us only to human intelligence, which usually what artificial intelligence does. But you can think of machine learning as one branch of artificial intelligence, in the sense that we give the machine what we think is a way of learning. So learning is a cognitive task. It's a human intelligent task. We want to give the system this task, so we're doing artificial intelligence, but it's a very specific one. It's about how we learn from examples. Okay? So what you see here is something that is called, and rightly so, a spaghetti model. So this is a model describing the various possibilities of patients going through the hospital. But it can also be the very different ways of this lady walking through the airport, or a bus driving through this city, or, and here I try to pull you away from the spatio-temporal domain, humans doing purchases over the internet. Okay, if I purchase now a certain book, what will be the next item that I'm going to buy? Or if I purchase now a certain element, am I heading towards building a bomb or towards doing farming? Okay, so the same thing can be represented in the same spaghetti model. And that means that we get data, and we get a lot of data, and that's why machine learning is flourishing, because we have many different ways of getting lots of data these days. This is another type of representation of data. This has to do with the transportation. So each dot here represents a location of a bus. And we also added the color scheme on top of that. Green means that there is no congestion, and red means that there is some congestion in that specific element. But the fact is that we can know where buses are using sensors that are located on the bus, the same way that we can tell where a patient is simply by putting these beamers, an RTLS system that will tell us where the patients are. Okay. Now, as I've said before, with machine learning, just like an AI, we have a model, and then we have a reasoning mechanism. And this reasoning mechanism is a learning algorithm or a learning device. So each of these learning machines that we have can represent some way of us thinking of how do we learn. So this is a task that I'm going to present now, a task that is called classification. So basically, I'm trying to classify a new instance based on previous knowledge that I got from data. And an easy way to illustrate it, and it's not the only way, there are many tools for classification, is called a decision tree. Again, it's a tree, but in computer science terms. So we start from the root. The root is at the beginning. And the first element there says start hour. So let's say we want to know how long we're going to stay on a bus, in an emergency room, what have you. And based on previous data, the algorithm learned that the important element of how long we stay is when we arrived at the system. Again, a very simple example. So start hour means where did you arrive, and then there are decisions to be taken. If you arrived before the hour of 9.87, so quarter to 10 maybe, then you're going to wait for 72 minutes. If you arrive after that, you need to tell the system, is it before 3:30 in the afternoon or after? If it's before, it's 50 minutes. If after, it's 60. Okay, that's the mechanism of a decision tree. So because this is kind of an introductory talk, I'm not going to talk about how you do this with the decision tree, what will be the specific functions you're going to use, and so on. This is the outcome. This is what I have. Okay. Now, sometimes a decision tree is not good enough. It has its own drawbacks. So we can take that and advance it into something that maybe we call a random forest. And the random forest is basically tries to handle a situation where you have too much data and you don't have enough time or other resources to learn. So you sample from the data. And there are different problems of sampling from data. You can get different biases on that. So to solve that, instead of sampling once, you sample multiple times. Each time you sample, you run a decision tree learning, and you may get a different tree. So what we have here is like 6 different trees, and they're called a forest because this is not a tree, okay? And they are called random because you do this random selection of data from it, and you get these different trees. Okay, here I need you to stay with me. Okay. Now, once I have these multiple trees, I have to understand what I'm going to do with them. Because when I had a single tree, that's fine. You go into the system, you know what's the start time, you know where you're going to head. But what do I do with random trees? So with this random forest, you can do basically one of two things. One is to somehow aggregate them, put them one over the other, and figuring out a new tree that is somehow a combination of that. So we call this bagging. It can be called in different ways as well. Another way is to try to learn from each tree something that will be important for the next tree. Okay, so we're not just doing it by sampling differently and then aggregating together, but as you see, the line that leads here from one tree to the other means that in the next tree, I'm also learning from the previous tree and not just from the new sample of data. And by that, sometimes I can create a better model and do it faster. Okay? So we had the decision tree, we had the random forest, we had 2 ways of working with it. So why am I telling you that? Because I reached the point where I'm going to talk about who is the winner. And it's funny because when you speak with people and, I don't know, medical doctors, and you tell them, well, soon enough you will be replaced, or you will speak with the taxi driver and you say that, you will always get, not always, but most of the time you get the same response, which is, this is impossible. I mean, there's no way that I'm going to be replaced. On the other hand, if you talk to scientists, especially those that do popular talks, they will come and tell you in 10 years, 20 years, 50 years, whatever you sampled from the range between now and 100 years, you're going to say everything is replaceable, including data scientists, right? Because, you know, as soon as we give our intelligence to the world, an artificial intelligence will be created on top of that and will be replacing it. But what people miss is that basically there is no point in wasting any type of intelligence. I mean, artificial intelligence, obviously you're going to use, and machine learning you're going to use, but there is no point in wasting the human intelligence in the loop. And the way I like to think about it is human intelligence is like oil. Not in the sense that data is the new oil and so on, but it's something that took many years to establish. So for many generations, people were thinking about this problem of a lady walks into an airport. Well, maybe as long as airports existed. Or how do I help people go through the hospital fast enough? Or how do I get fast enough from one side of the city to the other side? Even if there were no buses, there were just like mail wagons, I still needed to handle this situation. So we have a pool of oil, which took a lot of time to use. And now I'm actually dipping into it and grabbing all these different elements of human intelligence and put them in the system. And surprisingly, this really helps a lot for, in this specific task, for the machine to learn. So remember this thing that I've shown you before, that basically we're going to use trips that happened before to guess or to predict how long it's going to take us now. So one of the features that we put in, and in machine learning it's called features because these are the elements that help us in the learning, is what it says here, feature 3. This is the snapshot prediction. This is what I mentioned before. But as I mentioned already, if I did it at 6 a.m. and not at 9, and now it's 9 rush hour, then I'm in big trouble. So I'm going to add another feature, which is this feature 4 that basically tells me how long it took before the last feature. Also, we know that the day of week and the time of day really affects my prediction, so I'm going to put that as well. So some call it feature engineering, but you can think of feature engineering exactly in the way of transferring human intelligence into the artificial intelligence. Because we're not just getting data, we're getting data that we put in a context, and this context is very useful for us to learn better and faster. And, well, I'm talking a lot, but we also actually experimented with that. So we did a simple experiment. We took this decision tree based into random forest, okay? And we used this type of random forest analysis where each tree helps the next one. And we tried it once by just sampling random sample of the data, or we gave as a first understanding to the random forest our snapshot principle. So the snapshot principle is that human intelligence element putting into the loop. And we found out that we were able to identify a better tree in terms of prediction. So we were able to predict better in less time. Okay? So starting randomly from wherever your search space is, or starting from a place where humans tell you where to start, may make a lot of difference. You may find the right solution, you may find it faster, and so on. One thing to note here is that humans, when they bring their own solutions, they also come with their own biases. So this should be done in a very careful way. So it's not always, just take whatever human intelligence tells you and put it into the system as is. You need to, again, understand the cost that you're paying for going this way and not that way, and whether this solution will be able to generalize better if you do it with the human intelligence or without, and so on. But the main theme for me here is that by combining the human intelligence, maybe as a starting point for our machine learning algorithm, yields better results than without. And therefore, the winner is always to work together between the artificial intelligence and the human intelligence. Thank you. Okay, so here's the problem. You start collecting data, okay, and sometimes the data that you collect comes from some sensors or from some tables that exist on the web or whatever, and it gives you a specific type of data. It may or may not include the day of the week and the time of day. So without feature engineering, what you would do is you take everything that you have in your data, the raw data, and you put it into a machine learning algorithm, and some of them, depends on whether this is deep learning or not, will be able to generate these new features for you. But in general, once you get into a data problem, you have the data that you have, and the features may somehow needs to be created out of it. And that's the engineering. So the engineering, as with all other cases, will have, good practice. So you would say, okay, there are works now that talk about, if I work with numbers, here are the 200 different features that are most likely to help you. And then you create these 200, and then the feature engineering becomes a feature selection, because the algorithm can help you select the best ones. But in some different applications, if you don't think enough about it, then the machine will not be able to create that feature for you. The machine will be able to create other features that, as humans, we can never think about or understand about. There are nonlinear combinations of data and so on. But what we do is also something that the machine cannot do in this. So the feature engineering, I think this will be the place where the humans and machines will somehow interact together.
Thank you. It was a fascinating talk. I want to know, in your last point, you made an observation actually that by injecting the human intelligence into the process, you were able to create an improved decision tree. However, and you rightly said that there are biases by what I introduced as an additional feature. However, could you comment about cases where injecting the human intelligence actually created inferior decision trees?
So to understand why decisions are better or inferior, you need to understand a little bit more about how the machine learning algorithm works. And basically, it tries to optimize some kind of a measure. So you go to a certain spot, you say, this is my starting point. Maybe it's not good enough. I'm going to choose a trajectory that leads me to better results. The problem is that you can think of that as a territory that has lots of ups and downs. And there are many local optimum. And the algorithm may be stuck in some local optimum to say, from here I cannot move out. Now, if you start in a region, just randomly you chose a region that is really bad in this way, that it fluctuates, then you will not live. But if you start from another place where the human intelligence says, this is a good enough territory to start with, then the algorithm can optimize on top of it. So if you do the right choice, then it leads you to better results. If you do the wrong choice, it will lead you to worse results. And that's the way I see how it may also interfere. The biases is something different, because the biases just say, I'm injecting a completely wrong, not something that is not relevant to the problem, but something is completely wrong, simply because the way, this is how I think about it.
Could this way be, could we think of this interruption or distortion as a way of correcting the system so it would optimize a different behavior? So we can say, you want to maximize the time that it takes for the bus to drive through the city, or to minimize.
Yeah.
But maybe you also want to take into account pollution. And so that would actually intervene with that other goal, but you manually want to have that too.
Right. So the pollution in this case is the optimization criterion. It's not the understanding of how this system will work. To understand how the system will work, you have to say, okay, if I optimize for pollution, I know that buses that drive in constant speed will create less pollution than those that drive faster or slower. Then you say, oh, so let's try and do that by aligning the traffic lights with the bus, letting the bus drive, maybe slow down a little bit in a way that will not generate too much pollution, and then reaching the green light and then not have to stop. So there were works that were done that, but I would think about adding a new criterion as being, this is the optimization, but to work, but then you need to have this intelligence to understand what affects it. But I don't like the word correcting, because correcting immediately means that there is some tool, some X that does something, and Y that observes on top of it and decides whether this is right or wrong. And in many cases, we see that humans are not very good judges at that. So when I talk about working together, I really mean working together. So there is no one is better than the other. So humans will come and say, this is what I need to get the system done. I want to maximize my revenues, therefore I want a lot of traffic going my way in the shopping mall. That's fine. But I'm not looking at what the system does and say, this is wrong and therefore you need to fix it. So the role of humans in this game now is a little bit different. We are no longer judges. We are partners with the machine to work together towards this goal.
But that is something that is done, could only be done in the design room in the beginning, or is this a tweak that could actually be added in the process or ex-post?
I haven't thought about it. I think we can do both, but I haven't thought about it thoroughly.
I'm wondering whether these are solved problems when, in the long run, we won't need any human in the loop.
Okay, or any intelligence at all, for that matter. I don't know. I mean, maybe if we now think of a higher level, we say, okay, so my problem is to solve the problem of local optimum. And people worked on that, how you actually randomly jump out of local optimum and do that. And you say, by doing that, I actually can start from any random point and get to what I need to do. That's fine. We may also run out of oil. And that's, if you go with my idiom, then we may rely on the system in a way that we will no longer create new intelligence, new task. And sometimes when we look at our kids, we say, yes, this is how it's going to work. They're all going to listen to the machine. They're not going to generate anything of their own. So if we don't do that, we will run out of oil because no one will create new knowledge to solve problems. Somehow I believe that human curiosity will not allow us to do that because we will still be curious to do that. It's the only problem is that the next generation may not have the skill or the tools to do that, and that's something else that I guess we need to think about. But some of these problems may be just childhood problems, that's true.
Maybe just to follow up directly on that. So I guess most of the advancements that we saw in this field come from the past, 2 decades?
Less than that.
Last decade. So in the course of the history of statistics and computation, we saw incremental advancements, and suddenly the last decade was like an explosion of developments. And I wonder, do you think that we're still going up and expected to keep going up on this quick pace, or are we expected to see stopping?
So what we've seen in the past decade, this is a true revolution. This is no longer an evolution of stuff, and it came from two reasons. One is that we generated a technology that allows us to collect and store data. And then, using this technology, we started collecting and storing data. So before that, with statistics, we could have spoken on statistics as much as we want, but we didn't have the data to do that. As soon as I came to a problem and I said, I need to understand how humans, what do humans want in shopping? I had no data to work with it. I had small samples. So I had to guess a lot and overreact over things and so on. Now when I know exactly where the person is, when I know where they're looking at, when I can catch the brain waves or whatever you think about it, immediately I can put it into use. And I have the machine to work with it. So these two things together, the technology of allowing us to store and collect data and the data itself made this revolution happen. So obviously with that, as much as we're going to collect more data more and more, but if we don't have a new technology for storing data, we will run out of space of storing data, right? So people, there is a researcher at the Technion that talks about storing data in a DNA, because this is kind of a way of creating a new space to store data. But other than that, we think of the cloud now as something that is infinite. Well, it is finite. And at some point, the prices will be such that we will say, oh, we don't need to collect this data, but then we lose on something. So if there will be new technology that will allow us to store data better, to collect data better, then obviously the sky is the limit.
So last question.
Are ethical considerations factored into feature engineering? If so, how? Because, for example, if you take an example of an autonomous car in case of a potential accident, it will need to take a decision of whether to take an action that protects the pedestrian or protects the driver, or to hit a younger person or an older person. So how is that taken into account?
Right. So, actually, I think it's a good question. So it's feature. If we think of feature engineering as something that comes from humans, then obviously ethics needs to be taken into account, because let's say that the machine has no ethics. I mean, the machine is just a machine. The concept of being ethical is a human concept. But if we do the feature engineering, then yes, it comes back to us. And this is an interesting question, because we train now data scientists. We have an undergrad program in data science, and we have graduate programs in data science, and we actually give them the ability and the power to do stuff. We introduce one class on ethics. Okay, there's no stream of ethics courses. It's just one class of trying to give them some kind of a conscience, I would say, to understand to understand between right and wrong. But we know that throughout history, humans did good choices and bad choices. There were ethical people that were doing non-ethical actions, and so on and so forth. And the only thing I can hope for is that we educate them, and that we will get the right people in the right place when it comes to that feature engineering. But to sum up, the feature engineering being a human task needs to take into account ethical considerations.
Thank you very much.
Thank you. Thank you.